Good afternoon. So this is our 38th lecture, and in the previous lecture we have started our discussion on the multiple pipe networks. Today also we will continue the same, and along with this we will also try to see certain methods for measurement of flow rate when the fluids are flowing through the pipelines. So we had these multiple pipe systems, so pipes in series, pipes in parallel, and pipes in connected to a junction through the reservoirs. So we already did pipes in series. Now let's talk about pipes in parallel. So here what we have is we have a junction A and a junction B, and in between these two junctions there are three different pipelines, 1, 2 and 3. Okay. So typically if we are having this type of arrangement and we have to analyze the flow situations, then what will be the fundamental rules and how these will be applicable, that let's see. So at this junction A and junction B, we will be having the same pressure or same head. Okay. So what I can say that the delta H from A to B means change of head from junction A to B, that has to be equal to head loss in first pipe, equal to head loss in second pipe, and equal to head loss in third pipe. So it means that if you are having pipes connected in parallel in between the two junctions, then of course between the two junctions head loss will be the same. So through each pipe also head loss should be same. Okay. In this scenario, what happens basically, the distribution of the flow takes place into the individual pipes if their other characteristics are different, such as if their length is different, diameter is different, roughness is different, then accordingly the adjustment of the flow will be happening in individual pipes so as to keep the total head loss, the pressure drop or head loss in each pipe as the same. Okay, so that is the reason in this arrangement, because you can see clearly that the first pipe is completely straight and other two pipes are having certain curvature, so of course their lengths are to be different and they can have different diameters as well as the roughness, etc. Okay, so therefore what I am doing, whenever I am considering the flow rate through individual pipes, I am showing it as Q1, Q2 and Q3. Okay, so there are different flow rates in the individual pipes, and therefore what we will be finding, that total flow rate will be through this complete junction will be nothing but the sum of flow rates through the individual pipes. Okay, now on another way, if I simply consider only a single pipe section, then for single pipe section I can represent head loss, particularly the major frictional head loss, as FL by D V square by 2G. And in terms of flow rate, if I couple this velocity and diameter in such a way so that I can obtain a flow rate, then I can write it as F into Q square by C, where this constant C is nothing but pi square G D power 5 divided by 8L. So all these parameters, diameter of the pipe, length, pi and G, these are nothing but constants. So C I can call as an individual constant. Okay. Whenever, so this was only applicable for a single pipe. If I connect the head loss now to the total flow rate Q through this parallel junction, okay, so then I can represent this relation as Q square divided by summation of square root of Ci into Fi square, where Ci is nothing but pi square D Di square by 5 divided by 8 Li, and Fi will be the friction factor for individual pipe sections. Okay. Uh, of course, if we want to use, we can use this general form, but for majority of the flow situations, because this situation is very simple, so we need not to even remember this general form, we can analyze this problem fundamentally also, okay, by just equating these two first two equations. Okay, and if you have to find out the pressure drop, the flow rate through individual branch by using this generic relation, then it can be nearly approximated equal to Ci into head loss times Fi, friction factor of that particular pipe, and square root of the entire quantity. Okay, so we can see a problem based on this. So in the problem it is given that we have to assume that the same three pipes we are considering, which we did consider in the previous case. Okay, so in the previous case, particularly in the problem 1, we were having three different pipes of three different lengths and three different diameters, and at the same point of time their roughness was also different. So if you recall from the previous lecture, so you can see this was the table. So these are the three different pipes. So in the problem number 2 also we are considering the same set of three different pipes. Okay, but the only difference is that now these are in parallel arrangement with the same total head of 20.3 meters. Okay, and what we have to do, we have to compute the total flow rate Q neglecting the minor losses. So can you tell me how to approach this problem? We have to neglect minor losses. Now all these three pipes are in parallel arrangement, and we have to find the flow rate through the parallel junction. So can you tell me how to approach? So now we have total head loss of 20.3. Now all three pipes are in parallel arrangement. So what is the meaning? If I consider that, okay, this is my pipe 1, second is pipe 2, pipe 3, so all are at the same elevation level. So there is no change in elevation level. Okay, so it means that whatever the total head loss of 20.3 meters is there, this total head loss will be only equal to the frictional head loss in individual pipes. Okay, is this point clear? So that's why I can write this equation that 20.3 is equal to V1 square by 2G into 1250 into F1. And from where this 1250 is coming? This is coming from L by Q. Okay. Similarly, this is in the first pipe. So this has to be equal to head loss in the second pipe, and this has to be equal to head loss in the third pipe. So it means that I have got now three equations. If I equate this to this, then one equation, this to this second equation, and this to this is third equation. So I have three equations. But the only thing is that I have two unknowns in each equation. In each equation I have two unknowns, F1 and V1, here F2, V2 and F3 and V3. And also F has certain dependence upon V. Okay. But what I told you yesterday when we were doing the problem on pipes in series, that whenever we have to take the first guess of the F, we have to consider it for a totally rough design. Okay. The meaning of total rough design is that our Reynolds number dependence will not come on the friction factor. Okay, friction factor will be solely a function of relative roughness, and relative roughness is given in the question. So what I can do, I can immediately go to the Moody's diagram, and from the Moody's diagram I can find for the rough design what is the value of friction factor F1. Okay, so this is what I have done over here. So you can see this is the value of friction factor for first cases for the rough design is 0.0262. Correspond by substituting this, if you calculate V1, then V1 is coming out to be 3.49 meters per second. Okay. Once you have the velocity, now what you can do? You can calculate the Reynolds number. Okay. So if you calculate RE1 for the first pipe, it is coming to be 2,73,000. Okay. Once you have Reynolds number and the relative roughness both, then what you can do? You can once again calculate the new friction factor. So new friction factor you have calculated, which is now a function of both Reynolds number as well as the roughness. That is coming out to be 0.0267. Okay, is this one clear? Now again I can, corresponding to new friction factor, again I can compute the velocity, which is coming out to be 3.46 meters per second. So when we went from this iteration to next iteration, we found that our solution has converged. Okay, if our solution is not converged, then once again I have to calculate the Reynolds number, then again friction factor, again velocity. By convergence, meaning is that if this velocity and previous velocity, the difference between the two is less than some limit, say less than 0.05 or 0.5, something like that, we can set a convergence criteria. Okay, so based on that, what I can say that my solution has converged. So that's why if I have obtained the V1, I can calculate flow rate Q1 through my first pipe. Is this point clear?
So how did we guess initially the value of FL?
Value of FL initially we have guessed from the rough design of the Moody's diagram. So if you see, we had defined one particular reason in the Moody's diagram where epsilon plus is greater than 70. So when epsilon plus is greater than 70, then the variation of friction factor is line is completely horizontal and it does not depend upon the Reynolds number. So it solely depends upon the roughness, relative roughness. So we have the relative roughness known. Okay, so from the relative roughness data, we are just obtaining the value of friction factor for the totally rough region, for the initial case. Is this point clear? Then same thing I need to do for pipe number 2. Okay, so same thing I have done. First, for total rough regime I found this, corresponding V2 was 2.61. Then Reynolds number I calculated, then I corrected my friction factor, I obtained the corrected velocity and I considered this as the converged solution and obtained the volumetric flow rate. Okay, same thing I need to do for the third pipe. Okay, because this is a parallel arrangement, so this is something which I have done for the third pipe and I found flow rate of 11.4 meter cube per hour. Now what will be total flow rate? Total flow rate will be sum of all these three flow rates, because what we are considering the parallel arrangement. Let's say I have three pipes like this. Okay, so I have found the flow rate through this, flow rate through this, flow rate through this. So total flow rate will be nothing but sum of all these three, and that is what we are getting as 99.8 meter cube per hour. Okay, is this point clear? Now next case we can have is 3 reservoir pipe junction. Okay, so in case of 3 reservoir pipe junction, what we need to do, this is the junction. Is this point clear? So this is our junction, and this junction from through this pipe 1 is connected to one reservoir which is having elevation level Z1. Okay, through reservoir 3 it is connected through pipe 3 which is having elevation level Z3, and through reservoir 2 it is connected through this pipe 2. Okay, so how to solve this type of situation? So the very first thing what we can do is we can consider that at this junction point from all the pipes flow is coming towards the junction. That is the assumption we have made. Okay, what we have done, we have made an assumption that the flow at this junction from all the sides is into the junction. Okay, so you can see this arrow and this arrow all are showing that flow is coming into the junction. Okay, this is not fundamentally correct, because fundamentally if something is coming at the junction and junction is not either source or sink, then some equal amount should also go out. Okay, but what we are assuming from the analysis perspective, that every flow is entering into the junction. Okay, so by doing so, if I consider Q1 as the flow rate through pipe 1, Q2 as the flow rate through pipe 2 and Q3 as the flow rate through pipe 3, then Q1 plus Q2 plus Q3 has to be equal to 0. Is this point clear? Okay, everything is coming into the junction. Junction is neither a source nor a sink, so all these flows should has to be 0. Then second important point what we need to consider is we need to define the elevation or head at this junction. Okay, so what will be the head at this junction? Head at the junction point will be nothing but potential head of this. So say Zj is the potential head, and say Pj is the pressure at this junction point. If Pj is the pressure at the junction, then Pj plus Pj divided by rho g is nothing but static head. Okay, so static head plus potential head will make the total head or the total elevation at this junction point. Is this point clear? How Hj has come? Now what we need to do, we need to say that this Hj is something which is common elevation for all these three pipes. Okay, either you come through this pipe or through this pipe or through this pipe. Every time you will get same amount of Hj at this junction point. Is this one clear? Once I set this criteria, and if I consider that I am working in the gauge scale, and under the gauge scale if I say that all the reservoirs are having atmospheric pressure at their corresponding locations. So what I can do in gauge scale, this will be nothing but equal to 0. Okay. Now if I have to calculate head loss in first pipe, what will be head loss in first pipe? Say delta H1 is head loss in the first pipe. So delta H1 will be equal to F1 L1 V1 square by 2 GD1. This is the major loss. I am neglecting all the minor losses. And this head loss will be equal to head at this point minus head at this point. Is this one clear? So what is the head at this point? Head at this point is only Z1, because considering the gauge scale, static head at this point will be 0. Okay, so that's why I have written at this point my head is Z1 minus head at junction I have already defined as Hj. Is this one clear? Similarly, if I have to calculate head loss through pipe 2, what will be head loss through pipe 2? That will be FL V square by 2 GD for pipe 2, and that will be equal to head at this point. Head at this point. So what will be head at this point? Head at this point will be only Z2. So Z2 minus head at the junction. Head at the junction is Hj. Similarly, if I write for the third pipe, then head loss for third pipe has to be FL V square by 2 GD and head at this point minus head at the junction. So head at this point is only Z3. Okay, so Z3 minus Hj is my head. Is this point clear? All are clear with this idea? Now, if you have to solve the problem, how you can solve? You know the individual head losses, delta H1, delta H2, delta H3. You can know by using this equation. But in this equation, your F and V will be unknown. Okay. So, if you have to estimate this, you have to assume some value for Hj first. First, you have to make a guess of Hj. Corresponding to that, your right hand side will be known to you. Once right hand side is known to you, then you have only two unknowns, F and V. Then again you have to perform the iteration for F by considering it in the rough design. Okay. By this, you will be getting some value of F and V. You have got the value of V. From that value of V, what you have to do? You have to calculate the corresponding flow rates. Once you obtain these flow rates, then you have to substitute back into the first equation. And if this equation is satisfied, it means your guessed value of head is correct. If this equation is not satisfied, then you have to make another guess for the value of Hj. Is this point clear? So remember this point. Now you have to apply two iteration loops. One is iteration loop for Hj and other is iteration within the assumed value of Hj for F. Clear? All are clear with this idea? You will get better clarity when I will discuss the next example. So problem number 3 is, we have to take the same 3 pipes as in problem number 1. So pipes are same, but we have to assume that they are connected. They connect 3 reservoirs at these 3 elevations. So we have 3 reservoirs. The elevation of first reservoir is 20 meters, second reservoir is 100 meters, and third reservoir is 40 meters. Okay, and They are connecting these three reservoirs through a common junction. And what we have to do, we have to find the resulting flow rates in each pipe, and this we have to do by neglecting the minor losses. Okay, so what we need to do, tell me the first step. The very first step I need to do is, I need to assume the value of Hj. So let me assume that Hj is equal to Z3. So first guess I have taken that my Hj is equal to 40 meters. Okay, is this point clear? If my Hj is equal to 40 meters, then what will be happening? Now in the previous slide, everywhere I can substitute the value of Hj. Okay, once I substituted the value of Hj, Z1, Z2, Z3, these were also given in the question. So I have the value of constant. Okay, once I have the value of this constant, then I can now take the values of F1, F2 and F3 for the rough regime. And by knowing this F1, F2, F3 for the rough regime, I can calculate the value of V1, V2 and V3. Okay, so that is something which I have done over here. So this is the table. In this table, first Hj I have assumed equal to 40 meters. You can see over here all Hj values are 40, and corresponding to this Zi minus Hj value I have calculated, which is minus 20, 60 and 0 for three different pipes. Now when I have done this, then my this is head loss is coming equal to 0 for the third pipe. If head loss is 0 for the third pipe, it means that third pipe is not having any flow, because for flow to take place there should be some head loss. That's why third pipe will be having no value of friction factor, and corresponding value of velocity will be simply 0. Okay, and by knowing the values of F, these values of F are coming from which regime? These are coming from rough regime. Okay, these values of F are coming from the rough regime. By knowing only the relative roughness, and then I have calculated the values of velocity for pipe 1 and pipe 2. By knowing these values of velocity, I have calculated the corresponding values of flow rates for all the pipes. Once I have flow rates for all the pipes, I can do summation of these flow rates. Now summation of the flow rates is coming negative. What is the meaning of this? If summation of flow rates is negative, the meaning of this is that our guess value is not correct. If guess is correct, then we could have got the summation Q equal to 0. Okay, so now what I will do, because this condition is not being satisfied, so what I will do, I will make another guess. Let me consider, and of course if your Q value is coming negative, then you have to decrease your Hj value, and if Q value is coming positive, then you have to increase your Hj value. So over here, because my Q value is coming negative, so I need to decrease the Hj. So if I decrease Hj to 30 meters, then let's see what happens. What I have done now there is slight difference in the next iteration. First step is same, I assumed smaller value, I calculated Zi minus Hj. Okay, but now what I need to do, for these first two pipes, already from the previous iteration I have some velocity data known. If I have some velocity data known, it means I can calculate the corresponding Reynolds number. Once I calculate the Reynolds number, it means for these two values, now I can select friction factor by combined effect of Reynolds number as well as the relative roughness. Okay, so now the effect of Reynolds number is also introduced for calculation of first two friction factors. Fine, but third friction factor, because previous velocity was 0, so this I have to calculate for now the which regime? rough design. Is this one clear? And once I know these f, I can substitute back into my previous head equations and I can calculate the values of velocities. Okay. Now by calculating these velocities, you can see now summation of q is coming positive. It means if I have got positive, I have got negative, so 0 will be somewhere in between these. So how I can do calculate that at what xj my 0 will be? Now I can do linear interpolation. Okay, how I can do linear interpolation? I have the data of q. So q data 1 is summation q data 1 is minus 17. I want it to be 0 and other is 12.9. I have hj corresponding to 40 meters. I was getting minus 17. This hj I need to calculate and this was 30. Okay, so what I can do, I can apply the linear interpolation that hj minus 40 equal to 12.9 minus 17 divided by 30 minus 40 into 0 minus 7. So by doing this linear interpolation, I can calculate the value of hj where my flow should saturate. Okay, flow condition will be equal to this flow condition of summation q equal to 0 will be satisfied. So from here if you calculate hj, it will comes out close to 34.2 meters. Okay, so it will be coming close to 34.2 meters. So now what I will do, I will consider the value hj equal to 34.2 meters or 34.3 meters, and corresponding to this again I will do the whole analysis. Okay, so hj I have fixed, I calculated this. Now when I am calculating all these friction factors, so all these friction factors are including the effect of relative roughness as well as the Reynolds number, and Reynolds number is calculated by taking the velocities from the previous equation. Is this one clear? Okay, and that way you can calculate velocity and you will be getting summation q equal to 0.7. Still it is not exactly equal to 0, but 0.7 is very small. But if you still want to proceed further, because in particularly for pipe number 3, we have not got the second iteration for correction of friction factor. So if you want to get more accuracy, proceed further for the next iteration. Okay, and then you can get even more better value less than 0.7. Is this one clear? How you can get the better value, because now this is your positive. So from positive to negative if you want to go, so in place of 34.3 you can try 34.5. Okay, because then you will be increasing the value, then summation q will decrease. So this is how, if your multiple reservoirs are connected to a junction, then you need to solve it. Okay, so till now I have only considered a very simple situation where multiple reservoirs are connected to a junction. Now this arrangement can be more complicated. Let's say one reservoir is at this location, other is at this location, 4 reservoirs like this, and this type of complex pipe networks. Okay, so everywhere whatever the basic fundamental arrangements I explained to you, that will be followed. The very first thing is, when you are considering a junction, consider that all flows are towards the junction, and whenever you are considering towards the junction, then make summation and this will be equal to 0. One more thing I would like to mention over here, you can clearly see from the previous example that my first flow rate is coming negative. So the meaning is that in this example I considered all flows are approaching towards the junction, and this is coming negative to my assumption. So the meaning is, from pipe 2 and pipe 3 flow is coming towards the junction, but from pipe number 1 flow is going away from the junction. So you can clearly say that the reservoirs which are connected to pipe 2 and 3, from there fluid is going out, but the reservoir which is connected to pipe 1, that is actually taking intake of the fluid. Okay, is this point clear? And another important point is whenever you are having this type of flow, so this type of flow you can pipe network you can distribute into the closed loops. So one is this loop 1, loop 2, loop 3 and loop 4. So inside each closed loop, if you make the summation of total head loss, that has to be equal to 0. So in a closed loop, so sum of the total head loss has to be equal to 0. So what you can do, you can write head loss for AB plus head loss for BD plus head loss for BF plus head loss for BA, and that you can equate simply equal to 0 by using these simple two rules. One is summation of all Q's at junction equal to 0, and second is sum of all head losses in a loop will be equal to 0. So these are the two fundamental equations which you need to apply in the complex pipe networks, and by applying these two, if you further follow the Moody's diagram for calculation of friction factor, you can solve the entire pipe network problems. Is this point clear? Whatever ideas I communicated, is it clear? And remember one thing, once you solve an individual loop, by solving the individual loop, if you have calculated some elevation at this junction, then you will be considering this as a known parameter for all other loops, because at junction, any junction, head loss for every branch will be considered as the same. And of course, if you satisfy this criteria that sum of all pressure drop in a loop equal to 0, then this criteria of same elevation at junction will be automatically satisfied. Okay, is this point clear? Okay, so we had enough discussion on the pipe networks and how to solve different scenarios by individually specifying the pipes in series, parallel and at junction. Now, along with this, it also becomes important for internal flow problems to have some sort of arrangements which can experimentally give us the idea of velocity or volumetric flow rate which is flowing through a pipe network. Okay, so for doing so, the simplest arrangement is having restriction based flow meters. Okay, so if I consider a pipe, you can see a generic arrangement. This is my pipe. In this pipe, what I have done, I have created one artificial restriction over here. So you can see this is some restriction to the flow. Okay, so because of this restriction, what will be happening, whatever the flow is entering at section 1, that I am considering that say V1 is the average velocity of this flow. That's why I am showing this V1 velocity with equal arrow sizes. When this flow will be passing through the throat section, okay, so this section of reduced area is something which is called as the throat. That's why I have defined this diameter, the symbol for this diameter is dt, diameter at the throat section. Okay, and the previous diameter is d1, which is diameter at the inlet section. Fine. So whenever the flow will be passing through this throat section, we will be experiencing that there is convergence of the flow, and flow is converging, but it do not have minimum area at this point. Rather, it is having minimum area at the downstream of the throat, and this particular minimum area point is something which is called as vena contracta. Okay. So flow was entering, we provided one artificial restriction. Because of this restriction, flow has converged, and once the flow has converged, it is not forming minimum flow area at the throat, but it is forming minimum flow area further downstream, and the location corresponding to minimum minimum flow area is something which is called as vena contracta. And after this vena contracta formation, we will be finding through this dashed line, you can see that once again there will be further expansion of the flow. Okay, and above and below this region, you will be finding there will be some recirculatory fluid pockets, where some fluid medium is there which is continuously recirculating there itself only, and the whole bulk fluid which is entering, that is only passing through between the dashed lines. Is this point clear? So one important condition which we can say is that I can apply the Bernoulli equation between point 1 and point 2. Okay, what I can do, because point 1 and point 2 are very closely spaced to each other, so we can neglect all the frictional losses in this situation. Okay, so by making some assumptions, first assumption is that our flow is steady. Second assumption is flow is incompressible. Third assumption, there is no friction present. Okay, and by applying these assumptions, what I can say, and fourth assumption is that at point number 1 and point 2, streamlines are straight. Streamlines are straight at these points. Okay, because if streamlines are curved, then I cannot say that at the entire cross section of the pipe there will be same pressure. So for the same pressure condition to satisfy, streamlines must be straight. This is something which we have discussed earlier. If we have a curved streamline, then at two other ends of the streamline we will be having different pressure. Okay, but if we have the straight streamlines, then we will be having same pressure throughout the entire cross section. So the next assumption which we should consider is the section 1 and section 2 should be selected in such a way so that the streamlines are perfectly aligned to the pipe geometry. Okay, so if streamlines are perfectly aligned to the pipe geometry, what I can do, I can consider a pressure tapping over here and pressure tapping over here, and then I can measure the values of pressure P1 and pressure P2. Is this point clear? Because whatever will be the pressure at this point, same will be the pressure at the entire cross section if my streamlines are horizontal. Okay, all are clear with this idea? So by taking the help of this arrangement, if you are doing assignment, continue doing. I am not going to throw you out. You are doing assignment, na? So what we need to do now, we need to apply the Bernoulli equation, because whatever the assumptions we have made, these are nothing but satisfying the criteria of Bernoulli's equation. So P1 by rho plus alpha 1, at the moment you forget it, alpha is having some meaning, but say I am not going to discuss at the moment, so skip alpha 1 and alpha 2 at the moment. So let's consider that as per the Bernoulli's equation, P1 by rho plus V1 square by 2 plus GZ1 equal to P2 by rho plus V2 square by 2 plus GZ2. Okay, so now we have a horizontal pipe. Section 1 and 2 are at the same elevation level, so that's why GZ1 and GZ2 are actually cancelled out. Okay, and I can write from here that P1 minus P2 will be equal to, P1 minus P2 will be equal to rho by 2 times V2 square minus V1 square. Okay, now what I have done, V2 square I have taken common, and then inside what I will be getting 1 minus V1 by V2 whole square. Okay, now from the continuity equation I can write that A1 V1 is equal to A2 V2. So from here I can write that V1 by V2 will be equal to nothing but A2 by A1. Is this point clear? So from the continuity equation, V1 by V2 will become A2 by A1, and ultimately my P1 minus P2 will become rho V2 square by 2 into 1 minus A2 by A1 whole square. Okay, so from here if I have to calculate V2, V2 will become square root of 2 times P1 minus P2 by rho 1 minus A2 by A1 square. It clearly means that if I know the values of area at section 1 and area at section 2, okay, and if I know the values of corresponding pressure points, then I can calculate my velocity, average velocity of the flow. Okay, so if I know the average velocity of the flow V2, then I can calculate my mass flow rate as density into area into velocity. Okay, so rho 2 A2 into V2, which is equal to density times square root of V2 is 2 times P1 minus P2 rho 1 minus A2 by A1 and into A2. Is this point clear? Now, if you little bit further simplify this in terms of area, so then you will be getting that theoretical flow rate is equal to A2 by 1 minus A2 by A1 square into square root of 2 rho into P1 minus P2. So theoretically, this should be my mass flow rate of the fluid which is passing through this particular pipe. Fine. But in real scenarios, we will be finding that our actual mass flow rate will not be equal to the theoretical mass flow rate. That's why what we have to do, we have to multiply some coefficient over here to the theoretical mass flow rate in order to get the actual mass flow rate. So this particular coefficient is called as discharge coefficient. So this particular coefficient is called as discharge coefficient. Okay. So what I have done, whatever my theoretical flow rate was there, to this theoretical flow rate, I have multiplied some coefficient C. Okay. I multiplied some coefficient C such that I can get the value of my theoretical, I can get the value of my actual flow rate. Fine. So you can see, and one more thing I can do, another assumption which I have done over here, I selected this coefficient C in such a way so that the area A2 can be replaced with area of the throat. Okay, so if you see now, in place of using A2, what I am using is AT, where AT is nothing but area of the throat. Is this one clear? So theoretically, I should use A2, but within a pipe, it is not possible for us to identify the location or diameter of the vena contracta. Okay. Is this one clear? So, from into a opaque pipe, you cannot find the diameter of the vena contracta. But because this restriction we are providing by ourselves in the pipe section, so we can decide what is the diameter of the throat. Okay. So that's why it is important for the practical scenarios to use the diameter of the throat instead of using the diameter of the vena contracta. Okay, is this point clear? So that's why what I have done, when I was selecting this area, I have replaced A2 with AT and I multiplied some discharge coefficient which will be giving me some correction factor for modification of the area as well as for providing the considering the losses into account. Okay. Now this discharge coefficient we must calculate experimentally or using some semi-empirical techniques. Once we know the discharge coefficient for this type of restriction, then I can actually easily calculate the flow rate. Okay. Another simplification we can do, we can define one more factor beta which is equal to area of T divided by area of 1. So I have defined one more coefficient which is called as velocity correction factor. Okay, velocity defect factor or velocity correction factor. So beta I am defining as AT by A1. If my beta is AT by A1, then my actual mass flow rate will become C times AT into 1 minus, sorry, not AT by A1, I will be defining it as DT by D1. Diameter of throat divided by diameter of the pipe. Okay, so if I define diameter of throat by diameter of pipe as dt by d1 as velocity correction factor or velocity defect factor, then my actual mass flow rate will become C times AT by 1 minus beta power 4. Is this point clear? Now, one more thing what I can do, I can call this combination of C by 1 minus beta 4 as a joint coefficient K. where K is called as flow coefficient. So C by 1 minus beta 4, jointly I am calling something which is nothing but a flow coefficient, and flow coefficient is nothing but combination of the discharge coefficient and the velocity defect factor. Okay. So if I write this K, then I can write my actual mass flow rate is K times AT into square root of 2 rho P1 minus P2. Now for turbulent flows, the variation of C with Reynolds number is C equal to C infinity plus B by RE power Reynolds number, which is calculated based on D1 raised to power n, where B and n are the constants which are function of Reynolds number. Okay, and the flow geometry, and C infinity is the value of discharge coefficient for infinite Reynolds number. Infinite it is not, in reality we are going to the infinite value of the Reynolds number, but by meaning of infinite Reynolds number we mean that the value of the Reynolds number is extremely high. It means reaching into the extreme portion of the turbulent region. Okay. Similarly, K can also be written as K infinity plus 1 by 1 minus beta 4 B by Reynolds number power n. And this Reynolds number, and both these variations of C and K are only applicable for which regime? These are only applicable for the turbulent regime. Okay. Is this one clear? Now, this is one generic restriction I have shown. Now, for different application point of view, people have tried different types of restrictions for measuring the flow rate. Okay. So, what are the different possibilities for making these restrictions? These you can see over here. So, we can have three different types of restriction. One is called as orifice type restriction, second is called as flow nozzle, and third is called as venturi type restriction. You can see the corresponding schematic diagram. In case of orifice type restriction, you have a pipe and then you are having some protruded section which is giving some sudden contraction. No issue, I am completing in 5 minutes. This is in the same building. Huh? So what I am saying is, if this is our pipe, we are just using some protrusions like this. So that is called as orifice plate type protrusion. Okay. Then next we have this type of arrangement. This is called as flow nozzle type protrusion. And third is, if I have smooth converging section, then a section of constant diameter which is called as throat, and then I have enlarging section. So this type of device is called as venturi type device. Okay. And in terms of their head loss and initial cost, you can see the orifice type is having high head loss characteristics but low cost, low initial cost. For nozzle type, you will be having both intermediate head loss and intermediate cost. And for venturi type, you have both low cost as well as the, high cost as well as the low head loss. Fine. So these are the characteristics. So now, in between the initial cost and the head loss, we have to actually make some optimization. Why? Because one is signifying the operational cost, head loss is signifying the operational cost, which is being wasted in terms of pumping power. Okay, it's a continuous cost. And second, initial cost is determined in terms of the lifetime of the device. So that's why this is nothing but an optimization problem, and we have to optimize between the two in order to get the our that which type of device we can use for our requirements. Okay. Now we can see that if we are having orifice plate, so these are the designs as per the ASME standards. Okay, so as per the ASME standards, if you have to develop one orifice plate for pipe, so you have to consider that you can use pressure tappings in three ways. Either you can place one pressure tapping at D diameter upstream of the orifice plate, another pressure trap you can place at D by 2 downstream, Second, whatever the flange of the orifice plate is there, within the flange itself you can place two pressure tabs at a distance of 1 inch from the 1 inch from the orifice plate, and there can be corner pressure tappings for measurement of the pressure. Okay, so any of the three arrangements you can utilize when you are using the orifice type flow meters. And typically for this corner tap arrangement, if you have corner tapping, then for this arrangement your coefficient varies with beta and Reynolds number by using this particular correlation. But this correlation is applicable for values of beta within the range of 0.2 to 0.75 and for Reynolds number range of 10 to power 4 to 10 to power 7. And the variation of this coefficient is also shown over here as function of Reynolds number and as function of beta in this graph. So one important conclusion is, when your Reynolds number is greater than 10 to power 5, then we can say that almost this flow coefficient remains constant. But when our Reynolds number is less than 10 to power 5, then it is having joint dependence on the Reynolds number as well as the beta. Okay. Similar to this, we can have flow nozzle, and for flow nozzle we can put it inside a duct or we can put it inside a plenum chamber, and these are the corresponding value of the flow coefficients, and variation of flow coefficient as function of Reynolds number and beta is also shown over here. Here we can say that from Reynolds number greater than 10 to power 6, our flow coefficients are almost independent of the flow conditions. Okay, and then next we have, as per the ASME standards, these are the corresponding sizes of the flow nozzles. Okay, and then next about the details of Venturi I will quickly take up in the next class, and then we will start the next topic.